Hello. All right, welcome back to DSP. So before we start today's lecture, I'm sounding very loud. I might need to turn down the volume a little bit. So hold on. No, yeah, I'm fine. 0 dB. It's strange, it feels loud. Okay, so before we continue today's lecture, let me make a few announcements. First of all, this will be the second to the last week of lecture. Okay, next week will be the very last week of the lecture. But unfortunately, next week I apologize. I need to be absent because my son is graduating from high school. I mean, life is getting ever worse after that, after high school. But he's been attending the same school. It's like K to 12. 就是说他从幼稚园到高三都同一个学校啊。So it's a very special moment. So he's been staying in the same campus for 14 years, since age 5 to age 18 now. So it's a very special moment. So I apologize. I feel that I need to spend time. It's a time conflict. 上课不要吃东西啊，谢谢啊。I need to spend some time with him, but instead, I think whatever I don't finish today, I invite you to refer to last year's video recording because it's basically the same material. So if you agree, so I will not make extra effort to record a new video. So we will see how it goes today. Okay, so whatever that remains in this lecture, that will be the end of all materials that we want to cover in this semester. Okay, so that's the first announcement. And hope you agree. Yeah, please allow me to be absent. And the second announcement is that tomorrow's English discussion session, we have a guest from National Sun Yat-sen University in Kaohsiung. In the future, they will be known as Kaohsiung Zhongshan Daxue. Zhongshan Daxue. So she's an English professor, and so I applied to be observed. Okay, so you know that this is an EMI course. So according to the Ministry of Education, 教育部, they want some of us to be evaluated. They want some of our teachings to be evaluated. So we invited, so through some program, we invited a English professor from National Zhongshan University. By the way, she is also an alumni of NTHU. So she will be here on time, which is 4:30 in the afternoon for the English follow-up discussion session. And she'll be here to observe, just quietly observe what we are doing. So I already told her that this is going to be a discussion session. We have 2 problems, and up to 6 volunteers will show up on stage, and after that is a Q&A session. So please just feel comfortable. Just 把它当作它不存在. But this is part of the program that to kind of to show our commitment to teaching and learning. Yeah. So that's for tomorrow. Okay. Any question regarding my announcements? 下礼拜的我就不另外再录啊，我就看去年的影片啊，容许我这样子来完成我的任务啊。好 ，So if there's no further question, let's take a brief review of what we had last week. Okay, so remember the topic was to design still FR filter using the optimal design method, and so this is a kind of a important chain of 2 equations, equalities. So suppose that we are going to determine a FIR filter, symmetric type 1 filter, being symmetric. And suppose that the time is from minus big N to plus big N. And so therefore, all the samples, FIRs are impulse responses. All the samples that we need to determine are H0, H1, all the way to H big N. So we have N plus 1, a degree of freedom, 自由度, if you will. So, and then from there, because of symmetry, you can write down the frequency response as a function of omega, of course. And this is just nothing but our good old friend, DTFT, right? So this is a frequency response, but it turns out that we take a look, because cosine and omega can always be written as a polynomial of cosine omega. So the key idea is that let's change the variable. We will change the variable from omega to x. What is x? X equals cosine omega. X equals cosine omega. Make that change of variable first. Then any possible frequency response in this format, in this expression, can be rewritten, can be rearranged into a polynomial of x, where x is defined between -1 and 1, of course, because it's cosine omega, right? So we turn that into every possible, after the change of variable, every possible frequency response can be expressed as a polynomial up to n degree. Then, by now I hope that we all get the idea that optimal design means to find an argument among all possible polynomials, okay, among all possible nth order polynomials, find the one that minimizes the maximum error. What error? Weighted error, weighted absolute difference between your desired response and whatever design we have, okay? Desired versus reality. Okay, there is always a difference. Evaluate the maximum difference within all the bandwidth of our interest. Cosine f, that means pass band and stop band. Within those band of interest, find the best polynomial approximation to the desired response, now also expressed as a function of x. Okay, so that's kind of a nice summary in one slide. But then we introduce this interesting theorem, which tells us that mathematically the best one has to have some properties. The best one has to satisfy a few properties. So this theorem is by the name alternation. Why alternation? Because the best one needs to have at least n plus 2 distinct values in the x domain, such that if you just order these x values in ascending order, so to speak, from 小到大, in ascending order, in increasing order, order them like that. So this equality tells us that every next point, when we evaluate that weighted error, then every next point, the error changes sign. Okay, that's why this theorem is called alternation, 交错的 alternation, because the sign changes when we jump from one point to the next point. So the error has to go above, go under, go above, go under, if you remember that. Yeah. So that's alternation right there. And like the best one also, when you look at all these at least n plus 2 distinct values, they simultaneously reaches the maximum error. Okay, the maximum of error is simultaneously reached in at least n plus 2 distinct points. That's a property that tells us what kind of property the best one has to have. It needs to have this property. But now the next question is, so last week we looked at a few examples. So we look at the example as well as what's the insight. Whenever this theorem is not satisfied yet, that means you can visualize by inspection, there's still room for improvement. Okay, there's still room for, that's the insight. There's still room for improvement here. There's still room for improvement right here. If you look at it closely and right there, perhaps there's still. But since this one has no room for improvement, so this is the optimal one. Okay, and if you count the alternating point, 1, 2, 3, 4, 5, 6, 7, 8, 8 point for a fifth order polynomial. So 5 equals to 5 加3嘛, 5 plus 3. No, 8 equals to 5 plus 3. It's actually more than 5 plus 2, more than necessary. But this can happen. Okay, it doesn't always happen, but it can happen. This one turns out it is the optimal solution for a fifth order polynomial approximation to what kind of filter? What is this filter? Is it high pass or low pass? Do you remember? Now, after the transformation, right, when the x-axis is x, then cosine omega, So actually, on the left here is high frequency, there that's low frequency. This is actually a high pass filter. Okay, so this also tells us that a nice property about this method is that we can directly design a high pass filter without applying, so to speak, low pass to high pass transformation. Right, we can directly design a high pass filter or a low pass filter. So the design method is now unified. 好像是一个统一的架构, the framework is unified. But then stopping right here, last week, this slide just illustrates what does it mean to have an optimal solution, but it does not tell us yet. What does it not tell us yet? It hasn't told us yet how to find this polynomial, right? That's one thing. And the second thing is that after finding this polynomial, then we still need to go back to the omega domain to figure out the filter coefficients. Okay? So last week, I also briefly mentioned that even if we find, let's say, even we find the best polynomial, which equal to summation, whatever, a0 plus a1x plus blah, 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 an x to the nth power. This is the nth order polynomial. But then, with x equals to cosine omega, right? But then we know that this ought to be equal to our frequency response. The equality holds right here. If I remember correctly, 2 times summation k from 1 to big N, and here is what? hk, what? Cosine n omega, or should I say omega n? Yeah, either way is fine. Yeah, even if we find the polynomial somehow, which we are going to introduce how to find the polynomial by iteration, okay? But even when we find the polynomial, how do we figure out h1 to hk? Because these are the sample values that you need for convolution. FIR filter, right? So we still need to determine this. So technically, there is a sort of a hurdle. 这有点点障碍啊, sort of a hurdle, but not severely so. Yeah, 并不严重啊. But still, there's one more extra step to go back from X domain to the omega domain. So I just want you to be aware of that. Okay, but let's leave that because this is it's not most obvious. But I mean, this hurdle, 我用这个栅栏啊, this hurdle, 障碍或栅栏啊, 了解吗? This hurdle is not so much. Yeah. There's I can be very confident. I can confidently tell you that there's a one-to-one correspondence. Right? It's a one-to-one mapping between P and H space. The H space and P space. There's a one-to-one mapping. Once you find the polynomials, it's possible to go back to the H domain. Okay, to go back to the frequency domain. It's okay. It's doable. So not so much of a hurdle, but the hurdle is right there. So let's put that aside. So suppose that we figure this out. Okay. So let's not worry about this. Yet, but the more tricky, the harder, the more challenging problem is yet how do we achieve optimization, right? So far we only talk about that the optimal solution has to have this property, but we haven't discussed how to find this optimal solution, right? So next, let's introduce an algorithm. Let's introduce an algorithm, okay? This optimal approach, so first of all, let me read a few lines. To summarize, the optimal approximation approach, it provides a unified framework, as I just shared with you, 统一的一个架构, a unified framework for designing either low pass, high pass, or band pass, or anything in between, band reject, okay, and so on. Or even, I think it can even approximate like something like that, non-constant gain filter, if you will. I think, seriously, I think this is doable. Okay, think about it. Yeah, you can even approximate desired frequency response with a slope in the pass band, a slope in the stop band. I think it's doable. Yeah, although I've never tried it personally, I think this is doable. Okay, so it's a unified framework. That's the first point. And also, very nice property is that it gives us some flexibility to vary the tolerance level between different bands. Suppose you want a better approximation in the passband than the stopband. We don't care so much about stopband, but we care a little more that the precision in the passband. Okay, you can design that by you can accommodate that by giving different penalty factors. Okay, so this W, the way here tells us that when it's a higher right here, that means our tolerance is low. That means we want higher precision in the passband than the stopband. Okay, the final design will reflect that. 最后的 design 结果会反映出这个啊。The final design will reflect your setting about your setting of the tolerance or the penalty factor. Yeah, I call it the penalty factor. You know penalty? Penalty. Penalty kick. Anybody? PK 足球的那个12码球叫 penalty kick, right? Penalty factor. Okay, that's the way I describe it. All right, so it's good to know these nice properties of this design method. And right now, the final point on this slide, I'm going to share with you that in search of that optimal polynomial, the process involves 3 R steps and 1 S step. Okay, RRRS. Random guess, the first R, followed by refinement, followed by repeat the process until it converges, stopping criterion. Okay, so it's an iterative method. 是一个递回的方法 It's an iterative method, 3 R and 1 S. First, we make a random guess of the polynomial, interestingly, something like that. And when you randomly guess that, it's not going to be correct at the first try. But then, of course, we refine. Okay, this algorithm allows us to refine our solution and then repeat the process until it's getting better and better and better until everything stabilizes and then we have a stopping criterion. So let's take a look. This 3R1S algorithm has a name. It's called the PM algorithm, the Parks-McClellan algorithm. Okay. So this is just one slide. I hope it's big enough. So maybe I want to enlarge this. Okay, so taking a look. The first step is to make an initial guess. 先乱猜一下 make an initial guess. We want to guess L plus 2 extremal frequencies. I find it easier to talk about this in the X domain. Okay, so frequency means cosine means X. Okay, so if we allow me to stay in the X domain, and now the X goes from -1 for high frequency to +1 in low frequency. And in the middle, there's 0, which corresponds to, if you will, in the omega axis, 1 is DC, 0 is pi/2, and -1, that's pi, that's a Nyquist. Okay? So just make a, in between here, so x equals cosine omega. Right. So now let's work in the X domain. Make an initial guess of L plus 2 extremal frequency. Extremal 就是最大值最小值 means either maximum or minimum, alternating extremal points. So let's guess, suppose that we are going to design a filter that has a passband in the high frequency and followed by a stopband in low frequency. Suppose that we're going to design this high pass filter. Okay? And now the first step involves, let's tell me a number. What order do you want? Any order less than 8. Choose a number. 6? 6, okay, good. Suppose that we want to design n equals to 6. But according to that alternating theorem, we need at least 8 extremal points, right? So it turns out that 2 of the extremal points, turns out these 2. The edge frequencies of passband and stopband, they need to be included. Okay, it's yeah. So this is one, this is this one. So that's one extremal frequency. That's 这是内定的. Also, like how do you say? By default, they got to be there. Yeah. Otherwise, there's always room for improvement. So these two are the two extremal points. Let's suppose that we have, for the sake of simplicity, let's say our tolerance is the same for stop band and pass band. So these two got to assume that we are guessing that they are extreme points. So we need 6 more. Okay, we need 6 more, and with the cutoff frequency right at 2 pi over 2, right? Maybe I shouldn't just let me move this around. So it doesn't have to be symmetric. Let's say this is 稍微改一下免得 we don't mean to this can apply for any cutoff frequency. So let me move 2 over pi to the a bit to the left. So, but how about just making random guess? That's first step. Okay, so I'm gonna guess. How about 1, 2, 3, 4, 5, 6? I'm gonna guess these are the 8 extremal points that we need. Okay. So this got to be first one x1, x2. I'm going to guess x3 and this edge frequency x4, x5, followed by the 6th one, the 7th one, and the final one. So I'm going to guess that the final one is right at DC. Okay, just my guess. And from there, so we can write down now, compute the optimal delta. Right. So what does that mean? So we are going to, because these are extremal points, so we are going to assume that P x1 is oh, I'm being so stupid. I need to plot my tolerance right here. Okay, it's right there. Not down here. So that's a mistake. That's a mistake. So I'm going to assume that so here it will reach 1 minus delta, 1 plus delta. Okay. So for the error to alternate, so we need to go from above to under, right? Above to under, under to above. Let me use yet another color. Let me use green, or maybe red. So once we make a guess of all where these 8 points are located, and suppose that here, then we know that this is under, this is above, right? This is 1, this is 0, right? So the next point got to be under, so it needs to pass by here, and here, and here. And then from under to above, from above to under, from under to above. Okay, so we now have 1, 2, 3, 4, 5, 6, 7, 8. 8 points. 8 points. And we need to determine a fixed order polynomial to pass through all the 8 points. What that means? That means Px1 equals to 1 plus delta. Px2 equals to 1 minus delta, and so on. So let me just really complete the writing. Px3, again 1 plus delta because the error needs to alternate. P plus Px4, this needs to be equal to 1 minus delta. And now down to the 5th point, Px5 equals to what? P of x5 equal to 0 plus delta, going above. Okay. So now we will have 8 equations. And x1 to x8 is just your random guess for the first round. Okay, so now it seems that we have 8 equations. But how many unknowns? Can anyone tell me? How many unknowns do we have for the 8 equations?
8 unknowns. 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 8 unk
How many unknowns do we have? We're trying to remember that we are going to determine A, right? We are searching for the coefficients. So how many coefficients do we have? This is a sixth order polynomial, right? So how many unknowns do we have right here? How many unknown coefficients? 7, right? So we have 7 unknown coefficients, but wait, we have 8 equations. See, is that the problem? Do you see the problem, where the problem is? We have 7 unknowns, 7 unknown coefficients, but we have 8 equations. So now here is something, thank you for coming to the classroom. Turns out that the delta is also unknown. That delta is also unknown. So you see that that's the beauty of this algorithm. So exactly we have, by this theorem that gives a guideline, so we are going to make a guess, and we assume that the error will alternate, but turns out that delta is also unknown. What is delta? We don't know. So perfectly, we have now, good, we have 8 unknowns being A0 to A6, 7 coefficients plus delta, okay? 8 unknowns and 8 equations. So we can perfectly solve the set of 8 linear equations and find out the coefficients as well as delta. Okay? So in the end, you will obtain a polynomial, but delta is unknown. So it turns out that your polynomial may look like this. It doesn't necessarily, your polynomial may look like this, okay? So your polynomials, after solving the 8 equation, you will find the polynomial for sure, which passes through these 8 points, for sure. But now, what's next? What do you see right here? How do you see the problem we have right here? Now, this polynomial, is it really, of course, it's not optimal because x is a random guess, right? Our random guess is never correct at the beginning, okay? Right, so now, so even though this is 1 plus delta, 1 minus delta, 1 plus delta, 1 minus delta, but when we fit a polynomial, then that polynomial may have its extreme values elsewhere. The extreme values, the maximum minimums of this polynomial may not align with the random guess. Okay, so their extreme values occur at a different set of x locations, right? So it turns out that for this polynomial, after solving the equation, you obtain the polynomial, but its extreme point seems to be right here, slightly off, right here, slightly off. This might be aligned because it has to be right. But right here, not aligned, right there, not aligned, okay? The polynomial's extreme values may not be aligned. Extreme points may not be aligned with your initial random guess. In general, it will not be aligned, okay, at first. Then what do? Then we need to refine and repeat, okay? So in between that, let's summarize. Let's keep track of what we have so far. 3R1S, right? First, our random guess, easy, okay? Just make a random guess of 8 different points and solving 8 equations with 8 unknowns, you will find a polynomial. But this polynomial, indeed, it will pass through like the 8 points as indicated right there. But then the minimum and maximum places may not align with your initial guess. So what do? So the suggestion is, now, look. Take a look back at this flow chart, okay? Interpolate and get a polynomial, find its extrema, and retain the largest extrema. But here is a detail here. So sometimes when you fit the polynomial, it may have L plus 3 extrema, okay? even though I don't see how that can happen. I don't quite see how that can happen. But anyway, so now the key idea is to now update, make a refinement by using the extrema for the next round. Okay? You know what? At first, we were just making random guess where the extrema are. But now you really obtain a new set of extrema, so that gives us a clue how to update. Let's just call these new points the next round of x1 right here, x2 right there, x3 slightly off, that's okay, x3 right there, x4 is still happening on the edge, x4 equals to next round, x4, x5 is still right there, x6 also slightly moving to the right, so this is a new x6 and a new x7 and so on. x8 I'm not sure. So you get the idea. Once you find the polynomial and its extrema points may not be aligned with your initial guess, that's fine. Just refine. Just refine your selection of extrema points. Hopefully the next round will get better. Okay? So that's the idea. Retain the new set of extrema and then repeat. Okay? But before you repeat the process, here we see that the alignment is bad. It is not perfect. Okay? So we need to refine. Just retain the new set of minimum and maximum points, then repeat the entire process using the new x locations as your guess. Is that clear? Refine your guess by now you are sort of informed. Okay? You're a bit more informed. So maybe these new set of x points, a new set of 8 different x's might be a better guess. That's all. Yeah, it might be a better guess. Then we repeat, okay, and repeat and repeat. And hopefully, when do we stop? Hopefully, when we solve the equation, find the polynomial, and the polynomial's extremal points seem to align with your guess. What does that mean? When that happens, that means the two properties are simultaneously satisfied. Okay? When that happens, that means the alternating error and everything stabilizes, and we don't need to refine anymore. Yeah. So stopping criterion naturally. The stopping criterion is when everything stabilizes. When we check whether extremal point changed. If numerically they move by just 10 to the minus fourth, 如果它只是改变0.0001, if it's changed so little, then you can practically call a stop. The key idea is to refine your guess by a more informed decision. Okay? After solving for every round of finding a new polynomial, hopefully your selection of x points will be more and more ideal. More and more ideal until stopping criterion is satisfied. Let's say if the knowledge points change by more than epsilon, then we are happy. Okay? Then we practically obtain a nearly optimal solution. So that's the idea. And you get it? 有没有感觉? Can you feel it? Can you feel it? This is a very nice overall iteration method is a nice approach. It's in the heart of many different algorithms. If you cannot find the optimal solution, try to refine, to get better each time, right? And hopefully, you make a wish. You wish that your final solution, if the solution is getting better and better, maybe in the end we approach the best solution. Okay, that's kind of the engineering design spirit right there. Iteration method. Okay. Yeah, stopping criterion 3R1S. So I want to just confirm with you that I have an implementation, my own implementation of the algorithm. So I can share with you. I'm still debating whether this should be included in your last homework, but in the past it was a homework. Okay, so I wrote my own code. It's called my test PM. My test Parks-McClellan algorithm. I wrote it by myself before the AI era. Okay, I wrote it from scratch. Yeah, and there's also a Marchetti polynomial. Yeah, so I made my own implementation. So empirically, it converges in. Yeah, I forgot. It converges really fast. Yeah, practically. So this is a good algorithm. It has been discovered and is now part of the MATLAB filter design toolkit. Okay. Filter design at DSP toolbox. You can design optimal filters using MATLAB's implementation. Yeah. Okay, so that's about it. All I want to talk about in the very long topic of filter design. Yeah, over the past few weeks, we cover FIR, we cover IIR. Okay, this is the last slide on filter design. Yeah. So with that, maybe let's take a 2-minute break. Just relax, and I'm going to switch topic to the next lecture.其实这个有点奇怪哈，这应该要这样的。那才会是6节的。Okay. Okay, shall we move on to the next lecture? Okay, so for this lecture, we are going to look at yet another kind of Fourier transform by the name of short time Fourier transform. So the reason we need another kind of Fourier transform is, sadly, DTFT is not useful in many applications. Let me put it this way. So in a lot of time, nowadays, DSP, a lot of applications is kind of for retrieving information. Okay? Let's say you have a piece of even image or a piece of something, a piece of audio, a piece of speech recording, and we want to extract information. For example, speech recognition in real time, right? Extract information from recorded signals. That's a big class of applications. Or something called query by humming. Do you know what is humming? Humming 就是哼歌humming 最近有什么有趣的歌？ right, by humming. So which song is that, right? You use So there's actually more than 10 years ago, earlier in the era of DSP, we already have so many companies doing this, successful companies such as SoundHound.com. Okay, query humming, speech recognition, or automatic transcription of music, as we'll see an example. So I think the key issue, the key problem is that in the real world, sounds are not stationary. Not stationary. When you say look at the spectrum of your sound, okay? But what if your sound, sometimes it has this spectrum, and as time proceeds, in the next moment, the spectrum looks different. That's exactly how speech is happening, right? When we talk to somebody, your speech signal is never stationary. Right? It varies from one moment to the next moment, depending on what words are being said. Right? Signals in real world sounds are never stationary. 不平稳 or not stationary. However, the problem with DTFT is that it basically requires looking at all the time. It's an infinite sum over time. DTFT is looking at the entire signal as one thing. Okay, that's what DTFT is, right? DTFT. When we do DTFT, big X is equal to summation of what? N from minus infinity to infinity. That means we look at the entire signal, the entire time, and sum all the contribution to every frequency. So that's a limitation. Because in applications, you don't do this. You don't do this. So we need a different kind of Fourier transform. And the result, sort of a take-home message, the key idea I want you to get, is that we will be producing spectrogram. Spectrogram. Basically, we are going to turn a piece of recording, a sound recording, for the audio recording, for example, we're going to turn it into a two-dimensional image. Every recording signal can be turned into an image like that, okay? With x-axis being, horizontal axis being the time, and vertical axis being the frequency. So we are going to turn we can turn any piece of audio recording into a two-dimensional plot, where time goes from left to right, and at every time you see a spectrum. That's the idea. Now the spectrum can vary. So at every short time, like near here, you see a spectrum, and that spectrum is going to vary when you jump to the next frame. Okay, we have a different looking spectrum. Okay, so that's the idea, and the result is sometimes called spectrogram, or 视频图. Sometimes people make that translation. Spectrogram. Spectrogram. Okay. 图 Spectrogram. So that's an example. So I want to share with you this very nice example. It's a piece of work by a famous composer, George Gershwin, American composer, and this Rhapsody in Blue, 蓝色狂想曲. So let's listen to the music. Okay, yeah. So you can see that how do we read this spectrogram? Talking about information retrieval. Information retrieval. I'm going to say this word a lot. Information retrieval. How do we retrieve information now from this spectrogram? 这个叫什么？资料的 retrieval. Retrieve. 资讯什么？检索啊，谢谢。I don't like this translation though. Yeah. Sometimes it's 翻译成检索 it's translated into something like 检索 to 索取一些资讯索也说得通了yeah. Information retrieval, how as a computer, imagine you're a computer and you look at this spectrogram. Can you tell which music has been played? Can you tell at every moment which note is being played by that? I remember it's clarinet. 是一个单簧管Can you tell that? So when we just by inspection, it seems that it makes sense. Yeah, we have something that's going up, right? Something that's going up from low frequency to high frequency with some harmonics, okay? Because this is a musical instrument. So this plays really this curve, this trajectory corresponds to this the notes going up, an upgoing scale. 是一个往上的音阶You can see that. Yeah. Let's listen to the music again. I'm going to point to you where on the spectrogram at the same time, right? Yeah, seriously, this is sometimes I often tell my students, if you can tell by your eyes, if you can see it on the plot, then chances are you can automate the process and give it a fancy name somehow, right? So you get the idea. Information retrieval is so very nice that we have a two-dimensional plot, horizontal being time, vertical being frequency, and this representation, 这种表达方式 this representation exactly correspond to musical score, right? What do we have on musical score? Time going to the right, frequency going up, right? Exactly the same sort of organization. It makes a lot of sense, okay? So in the next few slides, we are going to study how to produce a plot like that, given a recorded signal, okay? For now, sort of we can just expect that we get something that's more useful than DTFT, okay? All right, so outline of today's lecture. So I apologize. So actually, our organizer we'll discuss short-time Fourier transform first. So that's the first part, followed by DFT and FFT. So let's look at what is short-time Fourier transform. Short-time Fourier transform has this expression, okay? Suppose that your signal is called x, okay? And we are going to use a window function, our good old friend, window, okay? It's going to be used right here. W is a window. Could be a Hahn window, Hamming window. I rarely see Kaiser window, but if you insist, a window function or just rectangular window, okay? The window that we introduced earlier elsewhere. So suppose that we have a window function and we're going to make this multiplication. We're going to fix the window but shift our signal to the left by m samples, okay? And then we calculate the DTFT. We're going to evaluate DTFT by the product between our window and our signal shifted to the left. So what does that mean? A window function may look like this. So this is a Hahn window, cosine square. No, I mean a sine square. Okay. Anyway, this is a Hahn window right there. And so window generally has a finite length, a finite number of non-zero points, finite length window. And we're going to fix the window but allow our signal to move to the left by m sample. The result now becomes a two-dimensional representation. That's all. It's pretty easy. Okay? We're going to shift our signal to the left. We're going to evaluate the spectrum in the future m's by looking at around sample m. Okay? And then the result is a spectrum. Still, this is actually this is still an extension of DTFT, but now moving to the left by moving center around the m sample in the time domain. The result is a two-dimensional representation of as a function of both the frequency and time. That's the definition of short-time Fourier transform. Okay, so I'm gonna sort of try to explain what's going on when we write down this mathematical expression. So suppose that so maybe after this we'll have another break, okay? So we have the cosine, the Hahn window right here, is fixed. But now we are going to move this, if this is our signal in the time domain, we are going to move the signal to the left, just gliding the signal through and further to the left. Now, whenever we move to the left by m samples, and at every moment we can evaluate, we can multiply the window with our signal. So that's why, Windows' job is to multiply with signal, right? With your signal. Okay, so still the window has the same job. So when it multiplies with the signal, then that allows us to just focus on this part, right? Because elsewhere is zero elsewhere for the window. So when we move the signal to the left, we are just focusing on a short period of time. And that's why this Fourier transform is called short-time Fourier transform. Okay? So it's like signal moving to the left, and through the window we are looking at a signal as the signal is passing by. The signal is passing by. Okay? So let's take a break of 10 minutes, and when we return, I'll share with you a story of my childhood, of looking at something passing by through a window. Okay, but that's after the break. 会告诉你小时候的一个故事啊。哦，会变。 Wait. Okay, so as I promised, I need to tell you a story from my childhood. But how do I turn this on? Oh, it's, okay, yeah. Okay, so I already sort of revealed my story. So the way I look at this mathematical definition is to consider a fixed window in this expression, and we are moving the signal to the left by m samples. And the result will give us a two-dimensional representation of a signal as a function of frequency, both frequency and time, short time Fourier transform. So x moving to the left, you're observing part of the signal using this window because the window has a finite duration or a finite width. So x is like, if you will, let me share my story. So when I grew up in 1970s, okay, I admit. So back in that time, when I was little, I lived in Banqiao. Anybody living in Banqiao? Anybody? Oh, from Banqiao, saying thank you. So I'm Banqiao Yongfeng near Guangren Zhongxue. And all time, like there's a lane like across the street from our apartment. So I live with my grandparents and all the uncles and aunts, 三代同堂. And like across the street, there is a relative, 我奶奶 of my grandma. So 我奶奶有一些亲戚住在对街and I envy them because their house is right by the railroad. Their house is right by the 纵贯线铁路 by the railroad, the main railroad. So like every 15 minutes there'll be a train passing by right behind there, and it's really loud, train, if you live right by the railroad. But as a little boy, I envy them because they can look at it, they can see the train all the time. So I envy them. So so it's like little Professor Liu looking through a window and waiting for the train to pass by. So what's the moral? 就是说，人在年轻的小朋友的时候，不会说那个看不起贫穷的亲戚。好，谢谢。Yeah, we have no bias against any of our relatives which might be not so rich. So I miss the old time. I don't know them anymore. My grandma's relative. And we back in the old days, everybody seems to be so happy. We just hang out with relatives and we can have a piece of 串门子以前的社会是这样你的亲戚住在铁路旁边没关系，还是好亲戚。So I miss the old time. Anyway, so maybe sorry it's not because it's so interesting to you. Anyway, imagine this is a window looking at something passing to the left. Okay? Signal is like a train passing to the left, and we are observing our signal by short duration, by one short frame each time. Sometimes this duration is called a frame. Okay? A frame. Signals which allows us to look at different part of our signal. Okay? All right, so now, next exercise. In the time domain, this is a recording I obtained a few years ago in a place I suppose that most of you have been there. Okay, so if you haven't heard the sound, 就我卖个关子you already opened the file. How many of you already opened the file and listened to the song example? 有没有谁已经有下载档案了？没有 So if no, then that's good. So let's take this next example. Okay, so it's an example of something that time domain. So we see a sequence of short pulses, maybe 8 pulses. And then after a pause, and we have another sequence of maybe 10 or 11 pulses. So that's in the time domain. But in the frequency domain, when we turn this into a two-dimensional representation, so now we are looking at both time and frequency axes all together. So now the advantage is that we can tell that, oh, these short pulses their energy seem to concentrate near 2 kilohertz. You can retrieve more information from here than by directly looking at the waveform. Okay. Do you see that? By directly looking at the waveform, we cannot tell the frequency. Yeah, you're just looking at the envelope. But by now, using short-time Fourier transform, we can analyze the spectrum when time goes by. Okay, so that's sort of a lot of extra information you can read, a lot of extra information you can retrieve from this two-dimensional representation. Yeah, okay. So a sequence of pulses center around 2 kilohertz. And does anybody want to guess what is this sound? A place. What is this sound? 8 pulses within 1 second. What is that? Da, 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 da. Da, 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 da. What is that? Anybody want? Yeah. 电钻. Da, 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 da. Oh no. Good guess. Helicopter. Da, 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 da. No, thank you. Who else? 2000 hertz. Yeah. iPhone 闹钟是哪一个闹钟？Good. Yeah. So, this is not natural sound. Okay. Yeah. But not iPhone. Yeah. Anybody else? Yeah. Gunshot. Da, 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 da. I don't think gunshot is 2000 hertz. No, thank you. In Taipei, no. This is recorded by myself. Yeah, no. Who else? Yeah. Da 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 da. Yeah. Who else? Yeah. Anybody? Yeah. Anybody? Gunshot. 电动打太多。Anybody? Maybe one last shot. One last. Anybody want to make one last guess? 这是什么？What is that? What is that? Should I play the sound? Okay, yeah. It's Taipei MRT. 2000 hertz sounds like this. Yeah, so when you go home, next time tell your friends that Taipei MRT, that sounds 2000 hertz. Why? Because we look at the short-time Fourier transform, okay? Yeah. Another thing to notice is that somehow in my recording, there's nothing above 16 kilohertz. And this might be because I recorded it using my iPhone, which already performs data compression. 可能有些类似 MP3, something like that. So this is not natural, but this is natural. Energy center around 2000 hertz is from Taipei MRT. And the next slide. So this slide is maybe not so clear. So now there's an issue of some detail about the window. The window has a length. Okay. So when we say big X as a function of both the frequency and time equals to summation over all n, W of n, X of shifting to the left by n samples, and otherwise we're doing DTFT. We're still using that same definition. But what we haven't specified is the length of W. The length of W, like that, if we use a Hahn window, how long is the window? How long is the window? So let's say from 0 to L. How long is your window? So actually, the length of window, if you use a long window versus short window, it affects the result. Of course, it does. So short-time Fourier transform, strictly speaking, you need to specify your window, okay, somewhere, because the result will differ when we choose a different type of window, when you choose a different length of window. Okay, so here's an example. In this example, on the left, we have a window length of 1024. On the right, it's 4096. So what do we see? When we extend the window length, then we are looking at a longer chunk of signal at a time. Okay? Every frame becomes longer, then the time domain resolution becomes more blurry. Here, in the time domain, the resolution 看起来比较清楚. On the left, the time domain resolution is higher than on the right, because on the right, when the window is long, we are averaging things out. Things are being averaged, more so than a short window. So choosing the size of window is something that you need to determine. Okay, when we visualize short-time Fourier transform, first of all we never talked about the phase. Okay, secondly, this is what I want to say. Time and frequency resolution of your two-dimensional representation actually depends on the choice of window. The next example might be clearer. Okay, so in the next example, still this is also from type A MRT. So type A MRT, so you see da 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 da. Okay. But on the left, we have a rather short window. On the right, 1024. What do you see? What's the difference? What's the difference between the two plots? What's the difference? What's the difference? What's the difference between these two plots? Anybody? What can you see? 宋佳颖，你说啊。What's the difference between this plot and 每次我拿出来就没电了。对， that's the main difference. So the one here, if you look at the lines, we have thicker lines here, but here the lines are thinner. Why? Because when we look at a longer period of time, then we increase the frequency resolution. It's a kind of a trade-off, okay? So when we use a long period of, assume that the signal is quasi-stationary. In this example, because the signal is quite stationary, that's very stationary, right? That's very stationary, okay? So choose any window. If you just increase the window length, it will give you a finer resolution in the frequency domain. That makes sense? It's a duality of Fourier transform. Okay? Longer in time, thinner in frequency. So, I mean, exactly how your spectrum looks depends on your choice of window, especially the length of window. That's a parameter that we all need to determine. Okay, so here's the summary. Sounds, hopefully by now you get the idea that sounds are time-varying spectra as we hear them. Okay, sounds are time-varying spectra. And the one way to visualize them, this hearing process, is to first represent your signal in 2 dimensions. Okay? In 2 dimensions. And next, there's an issue right here. Okay? Next, when we finally visualize that 2-dimensional plot, we know that it's plotted in pixels. 是一个个 pixel 画的嘛, right? No doubt about that, right? But here, turned out that m is discrete, but the omega is continuous. So it's not yet exactly what's being plotted on the computer screen, okay? So in the next few slides, we are going to introduce a discrete Fourier transform, which allows us to also consider frequency domain in discrete frequency lines. Okay? 就是频率也必须要离散化. Because when you store the result, it got to be in an array. So every pixel is one element, right? So to do that, we need to discretize both time and frequency. But here, the definition is not discretizing the frequency yet, right? Not yet. So in the next, let's study the discrete Fourier transform. So by the name discrete Fourier transform, the idea now is to first consider a block of signal. A block of signal that has a length of L. So the samples are represented by S0, S1, all the way to SL minus 1. And we assume that it's a column vector by taking the transpose. So that's my notation, linear algebra notation. So the idea that we take a signal, a block of signal containing L point, and make it a column vector. And make it a column vector S0, x1, all the way to SL minus 1. So this is a column vector, an Lth dimensional column vector. And now DFT. Still, I'm going to use the notation that small s is in the time domain, big S in the frequency domain. Okay, we still follow this convention. The DFT is defined as follows. This is the formula, the expression for DFT, discrete Fourier transform. So when we take a look, so there are many different ways to look at this definition. But what do you see? So still, this is going from time domain to the frequency domain. Now, frequency has an index. Now the frequency becomes the frequency variable becomes an index. Okay, so and the index goes from 0, also from 0 to L minus 1. Okay, so maybe let's write it down. Big S, okay, the kth frequency line equals to a summation in the time domain S, and then you do an inner product of S with what? With E j k times the fundamental frequency. That's the way I look at it. Okay? K times the fundamental frequency, where the 2 pi divided by L can be regarded the fundamental frequency 是一个基础频率啊。Fundamental frequency. Because 2 pi divided by L, what is that? It corresponds to the frequency which complete one period in L points, right? So that's the fundamental frequency. If the total length of your block is L, then 2 pi divided by L is a frequency for the signal which has which completes one period in L points. And then we are basically changing from time domain to the frequency domain by considering how much of component it has at k times the fundamental frequency, and the result is called the kth frequency line, kth frequency line. Okay. So in this definition, obviously k is discretized. K is an index. 它这是一个指标了。K is an index which go from 0 to L minus 1, same as in the time domain. Same as in the time domain. So this definition gives us a linear transformation. So this definition turns out it gives us a linear transformation from time domain to the frequency domain. And the dimension is L. Okay? We have an L-dimensional time domain, and after the transformation, we go to the frequency domain. And in the frequency domain is indexed, and the frequency domain also has the same L dimensions. Yeah? Can you feel it? This is a linear transformation. A linear transformation. So there are there are a few remarks. First remark, why is this called discrete Fourier transform? The answer is because discrete Fourier transform is DTFT sampled in frequency. Discrete Fourier transform, the DFT, is basically DTFT evaluated at omega equals to k times the fundamental frequency. Should I repeat it? Okay. DFT is DTFT evaluated at k times the fundamental frequency. Yeah. And therefore, it's called DFT. Because now the frequency is also discretized. 也被离散化了. The frequency is also discretized. So that's the first remark. The reason why this is called DFT. So it's like, remember, previously we talked about the relation between DTFT and Z transform. Do you remember that? We said something similar. We said DTFT is Z transform evaluated on the unit circle, right? But now further, if DTFT is if our new thing is DTFT evaluated at discrete points, that means equally spaced points on the unit circle, okay? So here on the right, we have an example of 9 points DFT. Suppose that we are looking at 9 points in the time domain as a block. Suppose that we have a block of 9 points, and then when we turn this into the frequency domain, we get 1, 2, 3, 4, 5, 6, 7, 9. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 9 points. 9 spectral lines when we convert to the frequency domain. Okay, and these 9 spectral lines turns out to be DTFT sampled in the frequency domain. So the solid line 实线的部分 of the solid line is DTFT. Now your discrete FT can be regarded as DTFT sampled in frequency. Or the opposite. You can say that, well, DTFT is DFT interpolated in the frequency domain. So I'm not going to stress this point, but DTFT can be regarded as the limit of DFT when L approaches infinity. Okay, when the length approaches infinity, we are looking at more and more points at a time. Eventually, DFT approaches DTFT when L approaches infinity. Okay, so that's a pretty simple stuff. Don't worry about too much on that. But this is kind of the main message I want to deliver today. Okay. Remember that I mentioned that discrete Fourier transform is a linear transformation. And it's defined on an L-dimensional space, and it goes to another L-dimensional space. Okay, so basically DFT, if you will, DFT is something that maps. Let me just say CL to CL, of length L. DFT is a linear transformation that maps that goes from one domain to another domain, and we know that we know that every linear transformation can be represented by a matrix. I hope that you recall that any linear transformation of finite dimensions can be represented as a matrix. Okay, and here actually because it's L-dimensional input, L-dimensional output, so we know that the matrix representation is going to be a square matrix. 它是一个方阵啊, it's a square matrix representation of DFT. So let's take a closer look. Let's define this big matrix F, which stands for Fourier transform. Define this matrix, if you see that it's a 1, 1, 1, all 1 on top, the first row. The second row is 1, and this is a factor W that's defined as e to the j fundamental frequency. Okay, W squared all the way, and the third row is W squared right here, fourth row W to the third power, and so on. Okay, so this is going to be a symmetric matrix, and the last element right here, if you do it carefully, the last element is W of raised to this power. Then, by this definition, you can examine that this is true. Okay, the following is true. Then, Fourier transform relates your time domain signal to your frequency domain spectrum with this simple identity. Big S equals to the matrix F multiplied by to the left from the left to your signal in time. Okay, so that's that. So now define this big matrix right here, F 1, 1, 1, 1, 1, 1, 1, 1, W, W to the L minus 1, 1, W square, something, you know, 1, let me write one more term, 1 to the third power, something, okay? Last row, 1, W to the L minus 1 power, something. Big matrix F. So now F times small s equals to discrete Fourier transform. So this is something that I keep in my mind. Okay, DFT is because, and this is true because we can do this because this is a linear transformation. You can easily check the definition. The transformation is linear. All right? I'm not sure if you can find this material on the textbook, but this is my handout. Okay, this is how I see what's happening when we do DFT. It making sense? Yeah. Does it make sense? For example, yeah, you can plug in any x value, s equals to big S 0, big S 1, the first frequency line, and all the way to the last frequency line, equals to small s being linearly transformed to go to the frequency domain. This mapping is a linear transformation represented by a square matrix. So having said that, so let me see. Meaning of this matrix multiplication. So first, note that here W equals to E K, no K, 2 pi divided by L. There must be a minus sign. And J, sorry, J is important. Do we have a minus sign right there? Yeah, okay. So a few properties. So first of all, as I mentioned, DFT is a linear transformation. And then if you look at the rows, all the columns, this is a symmetric matrix, right? You look at the rows, I find it more convenient to discuss the rows first, right? All the rows here, they are mutually orthogonal. They're mutually orthogonal. They're mutually orthogonal. So when we perform Fourier transform, and what does it mean to multiply a row with a column? What's the meaning? That means we are looking at inner products, right? So Fourier transform, in all different versions of Fourier transform, just over and over again, we are seeing this operation of trying to calculate the inner product. So this is a process of projection, right? We're projecting our signal by separately consider its inner product with each row. So that's the meaning of Fourier transform, especially for this DFT. So in this regard, DFT is easier to understand than DTFT, because if you know linear algebra, we're calculating inner products. So when we do that, note that these are mutually orthogonal rows. So what does that mean? They represent an orthogonal basis of this space. It's like XYZ, but only L dimensions, okay? So this is a change of basis. The original signal happens, it exists in an L-dimensional space, and every dimension is one sample value, right? But now we change the base. We change the base by projecting our signal to the new coordinate system. And this coordinate system is an orthogonal. I mean, every row is like x and y and z. They are perpendicular. X, y, z is 垂直的嘛, right? So here, every row can be thought of as a vector, and all the rows, they are mutually orthogonal, just like x, y, z, right? So this operation is a change of basis, which allows us to look at our signal from a different coordinate system. So that's the meaning of discrete Fourier transform. Okay. So I think this is a beautiful observation that you need to easily check that all the rows are indeed orthogonal. But I mean, yeah. Is that clear? Or yeah, or orthogonal. Yeah. All right. So as I mentioned, okay. So this is to summarize what I just said. DFT is a projection onto a new coordinate system. Each row represents a basis vector. Okay, change of basis. So now we're changing the basis to be this first vector, second vector, and we have a collection of L vectors. It's a change of basis. And we are calculating their inner products with our signal. By multiplying a row vector with a column vector, the result being a scalar. 是一个存量嘛, we're doing inner products all the time. So each dimension now corresponds to our decomposition into different frequencies. So you can say the first one is to, for example, the first one is to do the inner product of this first row vector with our signal. So that's what that happened. How did it happen? That gives us kind of sum of all the sample values. So this is the DC component. Frequency is 0. And the second row, when we use the second row to calculate inner product, then that gives us the component at the fundamental frequency, 2 pi divided by L, and so on. The third row corresponds to the component at the second harmonics, 2 times the fundamental frequency, and so on. This is a change of basis. This is a Fourier transform. It's a change of basis from time to frequency. So this is what I love about using the matrix to explain Fourier transform. After a while, it gets easier. Okay? It's actually easier than DTFT. It's actually easier because everything is finite dimensional. Okay? 都是有限维度的. Everything finite dimensional. So I think I'm going to end my lecture for now because the next part, let's briefly preview it. The next part is regarding the computation load. So let me refer you to my recorded video from last year. Okay, we can find it. So it turns out that DFT, when you calculate DFT using the matrix representation, you need to perform L squared times multiplication. That's a computation load. And this computation load turns out is not the best way to implement it. Okay, it's pretty slow. Computation load is pretty slow, and it turns out that we have something called fast Fourier transform. Okay, the fast Fourier transform is nothing but a faster version for implementing DFT, and it reduces the computation load from n squared, or should I say L squared, to L log 2 of L. It's a great reduction of computation load. Okay, and for example, the structure may look like this. Okay, so I'm not going to keep talking, but there are different implementation and some analysis, and then you can compute the inverse and so on. So, but I guess I'll leave it for today. Okay, so yeah. Okay, so when we come back tomorrow, please prepare to take it easy. Sign up as a volunteer if you haven't done so. Try it, and for next week, next Thursday I will be around. Next week on Thursday there will be our last discussion session for homework number 6 for the last homework, or I hope that the week after that is final exam, so it's going to end very soon. Sorry for mentioning that, but take it easy, all right? Stay healthy, stay optimistic, 保持乐观 yeah. And for those of you who are fourth-year students, congratulations, and I'll see you on the commencement. 小 B 点大 B 点，I'll be there. Okay. For 大四的 for Avinav, I know you're going there, right? Yeah. Okay. So. Yeah, so we will still meet next Thursday. Next week on Thursday, there will be one last discussion session, and yeah. So that's all. Please download the lecture slide. Thank you for being here. Wish you a yeah. See you tomorrow. Actually, yeah. See you tomorrow.